Okay. Now I promised, or I didn't promise exactly, but I said we weren't going to do anything with elliptical orbits, but it turns out that in considering potential energies and so forth on the role of potential energy, it comes about naturally and reinforces what we did last time with simple harmonic motion. I'd ask you to throw, but I'm afraid you'd throw it up against the ceiling again and I'd not be able to see it and that would break. Okay. Thank you. Thank you. Okay, so the only white things we're allowed to throw to me are unbreakable white things that won't damage anything up here. Okay. Anyhow, okay, so we are going to consider an elliptical orbit. So we've got a mass big M here and a mass little m here. I didn't write it before. But we're going to assume that big M is much greater than little m. Okay. So that if they were of equal mass, they would orbit like this. Okay, they'd orbit about the center of mass. The orbit will be about the center of mass. Okay, and if this is so much bigger than this, that the center of mass is effectively at the middle of this mass, then you don't have to worry about the motion of this mass. Okay, so we're going to use that model. Looks like you got the Earth with a mass of 6 times 10 to the 24th kilograms and a space probe with a mass of 10 to the 4th kilograms. Okay, this is almost 10 to the 21st times greater than this one. Center of mass is probably within centimeters of the center of the Earth. Okay, so again, this assumption allows us to assume that this thing remains stationary. And of course, that's the assumption when we do circular orbits too. Now, we have an elliptical orbit that I said we weren't going to work with, but again, you see how it fits in with what we did with simple harmonic motion. The apogee is the point of maximum distance from the mass. The perigee is the point of closest distance. R sub A, I'm going to use for the distance of the apogee, R sub P for the distance to the perigee, and V sub A for its velocity at the apogee. So I want to find velocity at the perigee given these four things, this, and this. We want to start, as I hinted, with potential energy. Remember how we did that with simple harmonic motion, okay? Potential energy is 1/2 kx squared at distance x. How do we get that? We use the definition of potential energy equal and opposite to the work done by this conservative force, okay? Relative to some point. Well, rho has all kinds of connotations, but we'll kind of ignore most of those connotations here. Some of them are appropriate. Rho could be a density. It could be the analog to the polar coordinate in polar coordinates. Okay, the radius R. But I'm using a different symbol here than I'm using here. because I don't want to confuse this symbol with this. It'd be like big G, big M, little m over r squared dr. But in any case, there it is. And that integral is negative big G, big M, little m over r. We did that in detail last week or the week before. So there's our potential energy function. Now, how are you going to use the potential energy function given the velocity at apogee to find the velocity at perigee? Well, we evaluate the potential energy function here and here. Okay, their potential energy at the 2 points. Right there's our energy situation. And the information we have is it applies to this point and this point. So what do? Well, we observe that the total mechanical energy is constant. Okay, there are no dissipative forces out there in space, or at least we ignore dissipative forces. And let's say we assume that. Assume that the dissipative forces in space are negligible. So what's your conclusion? Total energy at A is the total energy at T. Total energy doesn't change. Now let me state right now, if you know the velocity and distance at apogee, and you happen to know what the perigee is, this is going to work to give you the velocity at the perigee, okay? However, this distance and this velocity determine where the perigee is, and it might not be where I said it is, okay? There's another principle that you need to use to figure out where the perigee is and what its velocity is. So right now, we're doing sort of an oversimplified case. And this case is very, very simple. It's just total energy here equals total energy here, which means U of RA, I'll just use K for kinetic energy because that's what your text was. K at RA, that's not multiplication, that's function. K is a function of where you are, right? Your velocity is a function of where you are. Equals U of RP plus K of RP. Now, in this equation, what do you know? Well, right here it is, 3 things. You know this, And you know this. Okay. Not written too well, but you know what the symbols are going to be. Okay. You're just subtracting URP from this side. You put your own symbols on it. The concept is simple. It's simple. So 1/2 MVP squared equals big G big M little m over the negative big G big M little m over R A minus big G big M little m over RP that thing you can't read is just 1/2 MVA squared. In other words, the problem is solved. If I give you the numbers, you can calculate potential energy there. You can calculate potential energy here. And you calculate kinetic energy there. There are only 4 energies involved in the mechanical energy. 2 for this point, 2 for this point, right? You have potential and kinetic here. They add up to the same thing. Kinetic and potential add up to here. That's all you got to know. That's really easy. I mean, you got to understand total energy, but that's what I'm trying to get you to understand, because given the work I've gotten and everything else, I think it's the key to helping you do as well as possible in the exam. Okay. At this point, from what little information I really have, and from what I hear you saying, and from what I see you seeming to understand, and so forth. Okay. So that's why we're approaching it this way. Okay. So if I give you the numbers, you ought to be able to do that, right? Okay. Well, there's a little twist here. Angular velocity has to be constant. That's our angular momentum has to be constant, not angular velocity. Okay. So what would be the angular momentum at this point, and what would be the angular momentum at this point? Give me just a second to think about it, see if anything pops into your head. Since this is our last day of class, we'll have lab on Friday. This is our last day of class. Don't spend too much time letting you think. What do you think? I'll even pause for a second. Anybody have an idea about angular momentum? Okay, so we've got pretty good comments. You can see what the comment was, and let's make sure we're in focus because we weren't. Bring this back a little closer. The idea was that the angular momentum out here has to be the same as the angular momentum here. Okay. Angular momentum is involved with this distance. Okay. That's like your R vector. Okay. So that the further you are, the less velocity you need to have the same angular momentum you have here. Okay. Make sense? Okay, so let's write out what angular momentum is. Angular velocity is omega, right? Yep. Which equals r times v. Okay, is that right? Because the further you are, the more your velocity counts, and the more velocity you got. Okay. Also, definition of radian, that's in radians per second. This is in now wait a minute. What I'm saying, see what I mean about remembering formulas? Remember what they mean. Big overall. Okay. Because that's how many meters per second. That's how many meters per radian. You divide a meter per second by the meters per radian, you get radians per second. Okay. So you can go with units. Okay. So what I said before just didn't make any sense. Okay, anyhow, omega is V over R. And angular momentum is omega. Okay. Now, I think you have a cross product rule. You take your R vector and you cross it with your B vector. Okay. And you get your omega vector. But there's your angular momentum. So the concept here, the idea is the bigger, well, suppose we can say this is thing is, oh, okay, hang on. Something wasn't connecting because this should be equal to MVR, like your linear momentum times your radial distance, okay? And what's I? I is like your MR squared. If you do MR squared times V and divide it by R, you get MR squared V over R, which is MRV. And that might be the form you want to look at it. That you want to use to look at this picture. Okay. So angular momentum M R A V A equals M R P V P. Okay, that's I omega A, I omega P. Since we're just looking at the perigee and apogee, the angle between R and V matters. The cross product matters. But in this case, we can kind of simplify it because the velocity is perpendicular to the radial vector, okay? This implies that VA over VP equals RP over VA, meaning that your velocity is inversely proportional to how far you are. So if you're twice as close, you're going to be moving twice as fast. And I wrote G going up the right one. Okay. Now that coincides with the intuition that I just heard. Okay, but it puts it in a more solid footing. The intuition I just heard was basically the further you are, the more your velocity comes. So when you're in close, you're at a lesser distance, so you need more velocity to make up for the fact that you're closer. Okay, I forget exactly words in which it was said, but it comes down to that. And there it is in symbols. So over here, we can say observation of angular momentum says that LA equals LT. Now these are vectors. So you calculate these easily enough by saying that MVRA equals MVRP. Again, what I just wrote down there. And implies your velocity is inversely proportional to proximity. And this applies only to perigee and apogee. Which is where V and R are perpendicular. They're perpendicular. You got to use the R cross MV thing. All that just says you're twice as close, you're twice as fast. Okay. So velocity at T has to equal velocity at A times RA over RP. In this case, RA is the apogee. So RA over RP is going to be greater than 1. So velocity at the perigee is going to be greater than the velocity at the apogee. Make sense? Just a digression. One of the neatest things that's happened in the last 5 years was the Parker probe. Okay. And when that was launched, was it 3 years ago? Anyhow, when that was launched, you think you want the thing to go close to the sun, right? So you think you just set the thing out there in space and it'll fall right into the sun. Okay. Well, we're moving at about 30,000 miles an hour in a direction tangential to our orbit, right? So we're going 30,000 miles an hour this way, and we want something to go this way. If we just set it out there and let it go, if we could get it away from the Earth and just let it go, it would keep moving in this orbit. So we got to shoot it backwards at 30,000 miles an hour. I'm not sure we have a rocket that can do that. Okay. And you didn't really want it to drop into the sun. You want it to go into elliptical orbit around the sun where it gets close to the sun. And it's done that, and it's got some spectacular data that they haven't even begun to fully analyze. Because you get all this data, and then you got to figure out what in the world this data tells you is going on there. Okay, you got to use everything you know about electromagnetism and particle physics, and a whole lot of stuff. And the way they got it to go closer, they put it in orbit that didn't bring it all that close. Maybe kind of like the one you see. Okay. So like moving along the velocity of the Earth here, but we shoot it backwards, so we get it at a much lesser velocity. So now it has less mechanical energy. And it doesn't have enough kinetic energy to keep it at that distance anymore. Okay, so now it starts falling towards the sun, it comes in, and maybe it's kind of like this. Maybe it's kind of to this scale. I forget how close it got. I think on the first pass, we're 90 million miles, it's 30 million or something like that, maybe 3 times as close as the Earth. Okay. Near the orbit of Mercury, maybe. Now I'm just conjecturing, I don't remember. So it goes around the sun, and then you send it close to Venus to slow it down. So it swings in closer. And you do a couple of passes like that to where it finally gets, so Venus is moving around like this. You shoot it in front of Venus, and Venus pulls it backwards. That changes its mechanical energy. Okay. And keep changing its mechanical energy until it gets within like 10 million miles of the sun or something like that, which is inside the sun's atmosphere, pretty much. It's not inside the glowing part you see when you look at the sun. So we don't have anything that would survive that. Okay. But it gets plenty hot. You need a really good heat shield. Okay. So it's pretty cool. And that whole idea of having to shoot it backwards to even come close to hitting the sun. All right, anyhow, back to this. But this is very relevant to that particular thing. You ought to look that up. Oh, yeah, and the other thing is, just as we got to that in gravitation, just we got to orbits and gravitation's a daily shot it. So NASA's in tune with me. Okay. They didn't even ask me. They know how to read my mind. Something like that. Some sort of conspiracy theory. Okay. It was just a neat coincidence. But anyhow, there it is. The whole point of this is then that this VP has to match the VP you get from this equation. Okay? So the VP we get from this equation is VP equals 2 times all this stuff on the right, all divided by the mass, but the mass is going to divide out because it's a factor of every expression. So we get 2 times, well, let's make sure we get the signs right. Well, I'm going to do the times there. I'm going to factor out big G, big M, little m. I don't need the little m anymore. And it's going to be this plus 1/2 MVA squared. Now, this thing here, well, there's no negative sign in front of this. So this is going to have the sign of whatever this is. Okay, well, what's bigger, 1 over RP or 1 over RA? Tell me. Think 1 over RP is bigger? Give me this. Think 1 over RA is bigger? Give me this. I have various opinions. So far, it's split because Wesley hasn't. Oops, that's a guy out in the hall. Hasn't yet voted, but he's obviously thinking. Okay. Well, what's bigger, RP or RA? RA is bigger. I mean, they're in the picture, right? Your apogee is further than your perigee. Now you got to sort all that out. So it's kind of difficult to answer that question when you're on the spot. So I think everybody just flipped a coin since we got pretty much an even split. But RP is less than RA, so the reciprocal of RP is greater than the reciprocal of RA. Now you want to be able to think that. That should be something that's part of your thinking vocabulary, okay? Because as engineers, okay, if this thing gets smaller, does that thing get bigger or does it get smaller? Oh, it gets bigger. Okay, so now, okay, so we design it this way as opposed to that way. Now we'll work out the equations and see if I was right. Okay, does that make sense? If you're trying to think something through, you want to be able to think about proportionalities I've mentioned several times before. Again, it's a topic that people tend to be weak on, but it's really simple for somebody with your aptitude. Okay. I mean, I started thinking about it in 8th grade. You guys are deprived because your curriculum doesn't think about anything in 8th grade. Well, it does, but it thinks about too many things. I don't know how somebody develops a good sense of proportionality without being introduced to it when their brain is first big enough to comprehend the idea. But you can. So I kind of recommend it in your spare time. I know you got a lot of spare time, right? Okay, well, anyhow, I know you don't. So I know you're really pressed for time. So both of these conditions have to be satisfied. What this does is gives you 2 simultaneous equations. For VP. Okay. Now, I've read this fairly rigorous development of Einstein's general theory of relativity. The author says Now this is, general relativity is really pretty simple conceptually. I was at the point was that, okay, yeah, right. Okay, that's not simple conceptually. Okay, well, yeah, it is. About the third time I read through it, I said, oh, yeah, duh. So the only problem is there's so many symbols that it looks really nasty. And yeah, these equations are really hard to solve. But the idea is simple. Okay. Well, this isn't general relativity. What have we said here? Conservation of energy tells us in a very clear way that VP has to be related to VA this way, right? Okay. Here we've got two simultaneous equations. Both have to be satisfied for VP. Now we've got two simultaneous equations. That means we can solve these equations for any two variables so they're common. Okay? Does that make sense? We got one equation just from this simple intuition that the closer you are, the faster you have to be going in order to have the same angular momentum. Okay? We have another equation that tells us that to have conservation of energy, VP has to be this somewhat more complicated expression, but there's nothing mysterious about it. Where do these expressions come from? That's the kinetic energy at point A. That's a no-brainer. Okay? And remember, this is just a conservation of energy. Potential plus kinetic equals potential plus kinetic. You can calculate this, and this. This, and this. You can calculate the potential energy at any point if you know what this mass is, right? So you got two potential energies. All you need is one kinetic energy, and you can find the other one. Makes sense? That should. Take a note of that. Jot that down. Want me to say it again?
Yeah.
Okay, I heard yeah. Somebody said yeah as soon as they turned the photo on. Yeah, that's it. Total mechanical energy here equals total mechanical energy here. Total mechanical energy is potential plus kinetic at that point. Total mechanical energy here is potential plus kinetic at this point. We know the potential energy at any point if we know how far it is. So we have two of the four quantities. There are four quantities in the equation. Potential and kinetic energy at one point, potential and kinetic energy at the other point. These don't vary because dissipative forces in space are negligible. There's nothing out there to run into much. Okay? A little bit, and you got to allow for it depending on how close you are to the atmosphere of a planet, but let's not digress too much. Okay? Make sense? So there are only four things involved here. One is the kinetic energy out there, okay, which you can calculate because you know the mass and the velocity. The other is the kinetic energy in here, all right? So four things, three of which you know. The third thing is just 1/2 MVP squared. You can easily solve for it, okay? So again, the key is, first key is you know the potential energy function. Okay, that's a big key throughout both semesters of this course. It applied to the simple harmonic motion, the 1/2 kx squared thing. And the total mechanical energy is 1/2 Ka squared, where A is your maximum displacement, because that's where you stop and no kinetic energy. Okay. It's also equal to 1/2 mv max squared. So if you know V max, you know your total mechanical energy. Okay. Here, if you know V at any point, you know the total mechanical energy. If you know V here, or here, or here, or here, you know the total mechanical energy. You also know that the potential energy decreases as you get closer. Since the total mechanical energy doesn't change, that means the kinetic energy increases as you get closer. So in an elliptical orbit, you're slowest here, fastest here, and to go from here to here, you're constantly increasing your speed. Okay. How many of you seen the movie Apollo 11? If you think about this, as they're returning to Earth with this disabled spacecraft trying to survive, it's pretty cool. If you know the physics of the situation, it's awesome. Even if you don't know it, it's a great story, okay? But you have no idea how tough it was to make that happen. I mean, they pretty much show you, you know, here's all this trash that they have to work with. Their module's disabled. How are we going to get them back? You know, the engineers figure it out. Okay, for an engineer. So anyhow, you get what I'm trying to say? In a totally analogous situation for simple harmonic motion, but there's no sine wave involved here because you don't have a constant restoring or linear restoring force. Okay. You have a different potential energy function, which we get very easily by a very simple integral, a trivial integral. Okay. You guys are about to get into multivariable calculus. You all have been through differential equations, assuming you survive the next 10 days. Okay. And I think you will. Okay. Compare that to this function, which has nothing at all to do with this. One potential energy for one system doesn't equal the potential energy for another system. Okay. Go back to our rotating beam with the suspended weight over the pulleys. What's your potential energy there? Well, it's basically due to the suspended weight. So you do the potential energy with the point at which you release the weight or with respect to the floor, whatever's convenient. Okay, just know where your potential energy is measured from. This potential energy is measured from the x equals 0 point, the equilibrium point of your oscillator. This potential energy is measured relative to infinity because you're integrating from R to infinity. Okay, you're integrating the work done from R to infinity. The work done by the net force, since you're going in that direction and the net force is in this direction, is negative. So equal and opposite to that will be the positive, which gives you a negative, which is sort of confusing until you sort it out, which you might not have time to do, so just be careful. Okay? You have to understand that these potential energies for orbits are negative. You should ideally understand this so you can be rock solid certain of it. I don't think you're in a position yet to be rock solid certain 3 negative signs. Okay. That's pushing it for anybody. Okay. And sometimes I have to think through it. Okay. Even though I know what the result ought to be, I can easily write this down wrong. Okay. And here you got a couple of negative signs. Why? Because you put restoring force is negative kx. Okay. I'm using a dummy variable here, so it's not confused with this x. But it's that, and it's equal and opposite, so there's another negative sign. If you don't remember the definition, equal and opposite to the work done by the conservative force, guys, you're on your own. You better have a good memory for negative signs, okay? Because I'm not going to give you those formulas. Actually, I'm going to give you some stuff. Okay, so there are 3 situations right there. The beam with its potential energy function, okay? And of course, there's the unbalanced beam with its potential energy function. In the problems I've given you, we address that. If things unbalanced and it gets higher over here, then it's going to tend to rotate back to the point where the heavier side is lower, right? And in small oscillations, it's going to give you simple harmonic motion of an extended body. In other words, okay, an angular simple harmonic motion. The equations are identical. So you do have also equation for a physical pendulum or for that beam. U of R is the integral, negative the integral from 0 to theta of negative k theta. Well, we use same dummy variable. Okay, and it's the negative of that integral. One half k theta squared. This k has different units than this k. This k, when multiplied by x, gives you a force. This k, when multiplied by theta, gives you a torque. Okay? I'll put a couple more notes up here. This comes from tau net equals negative k theta. This comes from f net equals negative kx. Each of these gives you a differential equation that's trivial. You're about to take, most of you are about to take a differential equations final. Certainly, if you saw this differential equation on your final, you'd jump for joy. You know you're going to at least get 10 points. Okay, you're going to score. Well, I think you guys are going to do okay in your differential equations. But, and again, I only mentioned the differential equations because everybody is taking it or has had it. Okay, I wouldn't mention it in this course otherwise. I'd mention it because you can do it with first semester calculus, but you don't see it in its perspective until you've had differential equations. Okay, so what I've given you there is basically a summary of the potential energies for 2 forms of simple harmonic motion. The concepts and the mathematics are identical. It's just that for this one, you got to use moment of inertia and theta and omega and alpha and stuff like that. Okay, the angular quantities. And for this one, well, you're using the linear quantities, and we did all that last time. Okay. Well, we've got approximately 16 or 17 minutes left. So I talked about writing down some formulas for you. Again, let me emphasize this situation, a common situation where you have two constraints on this motion. Energy is conserved and angular momentum is conserved. Okay. Why is angular momentum conserved? Because whatever this thing is, the force is in the direction of big mass. So your R vector is zero. Your R vector for the moment, okay, the moment vector. There's zero moment of this force. It's aimed right at the center. There's no torque. Okay, no torque, no acceleration. But no torque, no change in angular momentum. I'm sorry. Except we got an acceleration. Try to put this in perspective. It's just, I think if you can really understand what I told you about these elliptical orbits, you've got a tool that's going to apply to a lot of different things. Okay. You've got a perspective. We get two simultaneous equations. They both have to be satisfied so we can determine what the shape of this orbit is, at least where the apogee and perigee are. And if you know that, you know the vertices of your ellipse and the focus, and you can get the equation of the ellipse. Just using pre-calculus. Okay. It never gets covered very well in pre-calculus. But it's at the pre-calculus level, it won't challenge you if you need it. You won't need it for this course. I'm going to ask you to find the equation that it is. I'd like to, but reality dictates that probably better not. The more important things you can get, which are these concepts. Okay. I have a lot of things I wanted to do, and I'm probably going to append this video at some point. Okay, probably not this afternoon, but probably tomorrow afternoon if I have the energy. Okay. If I don't have good energy, video just flat, uninspiring. They probably are anyway. Okay, now formulas. Now this is off the top of my head. This is what I would write. This is what I would recommend knowing. You can modify it any way you want. If you want to memorize 100 equations, you can. But you need to be able to navigate with less than 100 equations. I think a dozen or less, but we'll see what we come up with. Okay. Now, several of them. It's going to be more than a dozen. Conservative forces, what do we have? Now, I'm not going to write down equations, formulas. I'm going to write down expressions. You should know where these expressions go in what equations. And if you don't, it'll be a good exercise to figure it out, okay? And help you remember what the equations are. So you can do a little work, but you know, you can tell me what that is. That's a net force on a simple harmonic oscillator, right? So you should recognize that immediately. Now, well, it's a net torque on an angular simple harmonic oscillator, physical pendulum, or whatever. Okay. What's that? Rotational, right? These are conservative forces, common conservative forces, or conservative torque. And a conservative torque comes from a conservative force. I refuse to use MGH, but I'll use MGY. Okay. Again, if all you know is MGH, you're not going to know any of the important ones. Okay. And any of the more important ones, perhaps, at least for the purposes of doing well on an exam in this course. Okay. Although this is important, it's so obvious. I hate formulas because people get stuck on this and forget about this. Okay. Of course, these are okay now. And it will probably use negative mg. Okay. Potential energy. Notice there's no vector here. You might think about how the vector gives you a scalar. Those are some of the most important potential energy functions. We'll see that there are also potential energy functions for electrostatic forces and so forth. Okay, so here's potential energy. The most efficient way to understand these is to know how to apply the definition of conservative of potential energy as being equal and opposite to the work done by conservative force. If you do, you know what the integrals are, so you don't need to memorize these. On the other hand, if you know these, you take the negative derivative of each of these and get these. Okay? So if you want to have a compact set of things to be absolutely sure of, you could use either these or these. Okay? Now, these are so similar to these, though, that you probably, if you know one, you probably know both anyway. Okay? But be sure that you understand thoroughly one of them and how it gives you the other. That helps you think about the problem that you're confronting on the exam. Okay. We're using up a lot of time here. That's the recent stuff. Now, we also have these. Okay, the brain's not thinking as quick as it needs to. Trying to get comprehensive of these things. So for simple harmonic motion, in parentheses, this is related to this, this is related to this. Of course, you have 1/2 mv squared. You have f net dot delta s. You have f net delta t. If there's anything that you absolutely need here. I'm probably going to have to continue this after you leave to make sure I've got a functional set. Okay. But these are expressions. Again, where do they go and how do they combine with other expressions analyze circular orbits, motion from one circular orbit to another, etc. Okay. And I haven't talked about circular orbits in this review because we did that pretty thoroughly. And it really comes down to kind of this and this. Okay. And that tell you everything you need to know about circular orbits. At least a circular orbit about a smaller mass and about a much greater mass. 2-point mass is one much greater than the other. Okay, let's see. Time pressure, I got a minute left. Now, of course, I could list the equations of uniformly accelerated motion, which I assume you know thoroughly. But if you don't, I'll write down integral of A dt T1 T2. Equations of uniform motion, accelerated motion. And I'm going to rethink how I write that one, so I'll leave that off. Just telling you, that's your definition of work by the net force. That's your definition of impulse. Then, of course, you have delta KE or just delta K. You have delta P, which is a vector. And we're actually a little over time. So I'm going to stop there and I'll keep the video going. And after you leave, all the things digesting some of the videos, I'll wrap it up.